so the flip-flop timing information is really very important parameter to understand the working of flip-flop. Okay, so flip-flop, what the flip-flop timing is that we should understand. Let us try to see how it works. Suppose I have a data input, something like this from 0 to 1. And if the clock pulse, like, yeah, the clock pulse is changing from 0, 1, 0, 1, something like this. So there are some timing information that we should understand what the timing information is. The first time difference, like, see here, the data was enabled at this time. Okay, at this time state, the data was enabled. Okay, data initially the data was low, and the data input becomes 1 at this time instant. But even the data was enabled, but the clock was not enabled. Clock was enabled at this time state. So there is a time difference between these two, the data enabled and the clock enabling. So this time we call it the setup time. Okay, the time difference between the data. So the setup time is the minimum time interval that the data present immediately before the activation of clock. Okay, so this time is called the setup time. The second important point, like, once the clock is activated, okay, and then how much time the data is going to maintain at the same logic. Okay, so if you see here, even though the clock was activated and clock becomes logic low, but still the data was at the same state. It maintained the state for some period of time, and that time is called the hold state, hold time. This time is called the hold time. The hold time is the minimum time interval immediately after the activation of the clock pulse and until the data input is maintained at the same logic. Okay, at the same level. So that time difference is called the hold time. Okay, third and important parameter, like, once we have received the clock pulse, we got we have the data input and we have activated the clock pulse, then the output will be reflected, because see here, data input is activated, clock is activated, so definitely I will get the output that will be reflected after some time. Okay, so let us try to see the output is getting reflected something like this. Okay, so because it is not necessary that once we have the data is activated at this time and the clock is activated at this time, ideally the output should reflect immediately just after when the clock is activated. But whatever the logic circuit we have used, this has some delay, some internal delays are there, some propagation delay. So output will not be reflected immediately. It will take some time to get it reflected. Okay, and if it is taking some time to get it reflected, we need to come up with one more parameter, and that parameter, like time difference between the activation, like the of the clock pulse, and the time at which we are getting the change in the output, and that time difference is known as the propagation delay or flip-flop propagation delay, that is the TP. So these three timing parameters are really very important to understand. Okay, one more parameter that we can have, like TCH. TCH is means the pulse width of clock that it maintains for the high logic. So this time period, yeah, let me change the, yeah, we can make it. So this time period is nothing but this is the TCH. TCH, this is the time period at which it is maintaining the high pulse width, the high pulse. Similarly, we have another parameter, that is the TCL, and the low clock pulse width, like the clock pulse was low for that period of time, and then we can call it the TCL. So TCL is the time at which it is at logic low. The clock was at logic low. Okay, so this is how. One more thing, like that we need to, while calculating the maximum frequency of the operation of this from this flip-flop, we need to consider one more thing, like we need to also consider what is the delay of next state logic which we have connected after this logic. So suppose if I have a flip-flop, okay, and I want to calculate the maximum frequency of this flip-flop, so that also depends on how much propagation delay is there for the next logic. Suppose if I have provided the maximum frequency to this one, to this flip-flop, but the next logic which I have connected is not able to maintain the same frequency. Let us assume the delay of the secondary circuit which we have connected just after the flip-flop is very high. So that also comes in the picture, because that can get the properly process the output if it can maintain the same frequency kind of thing. Okay, so the delay of the secondary circuit or the next stage logic is also equally important to calculate what is the maximum frequency that we can apply to the flip-flop. If we are applying more than the delay of this frequency, so might be the second circuit which we have connected will not work perfectly. They will not be able to process, and even before processing the input, the next state will come. Okay, so it will not be able to will not get the exact output or the correct output. So to get the correct output, the next state delay is equally important to decide what should be the maximum frequency of the flip-flop. Okay, so the maximum frequency of the flip-flop that is decided with the help of some of the parameter, and one of the parameter is the next state logic delay as well. Okay, so if you see the T max, if we try to calculate the minimum clock period for the flip-flop, and that is given by the T must be greater than or is equal to TS, TP, and TNS. Okay, TS and TP is fine. TS is the setup time, how much it takes to set up, and TP is the propagation delay of the flip-flop individual element which we are considering, and the TNS is the delay of the next state logic. Because if next state logic is slow, then what will happen? The flip-flop will keep on changing, but the next step will not be able to perform the operation accordingly. So we need to consider how much delay is there, or delay in the next state is there, so that we can include all these things. And in total, we can call it the minimum clock period for the flip-flop. Okay, so this is nothing but this is a flip-flop. Yeah, so if I want to calculate the maximum frequency, so F maximum is nothing but it is 1 upon T. Okay, so whatever T we have calculated, this is how we can calculate the maximum frequency. So if we know the setup time, if we know the propagation delay of any D-latch or any of the latches, and we know the delay of the next state logic, so we can simply say that what is the maximum frequency that we can apply to that flip-flop. So this is important parameter that we should consider. Okay, so this is all about the flip-flop timing, and that's some of the important parameters that you should know. So if you have any doubt at any point, you can ask the questions here. Yeah, you can ask the question in between also. If you are unable to understand, you can ask in between. There's no problem. Okay.
Sir, can you explain this inequality?
Which one?
Sir, this inequality, sir, that you have written.
Here, this equation? Okay.
Yes, sir.
Okay, so let me repeat it again. Suppose I have a flip-flop. Okay. And I want to calculate the frequency of this flip-flop. Let us assume this is the flip-flop. And and this flip-flop is connected to some of the secondary logic. Okay, the next state. Let us assume next state logic, NSL, next state logic. Now what will happen? Because we know that on a flip-flop, suppose NSL is very slow. Okay, and the flip-flop is very fast. So what will happen? If I have provided a clock frequency of very high frequency, then what it will do? It will keep on changing the output, but this NSL will not be able to process accordingly, because the frequency of NSL is very less. Okay, so the delay is very high. So what it means? It means that the NSL delay is equally important. The delay of this next state logic is equally important to decide what is the frequency of this one and what is the time period of clock pulse that we need to connect at the flip-flop. Okay, so this is from where this TNS comes into the picture. Okay, so TNS TNS is nothing but is the delay of the next state logic. And if the next state logic is very fast, then yes, we can increase the frequency of the clock pulse, so that if we are changing the input, NSL will be able to hold those changes. Okay, so this is the TNS. Now let us talk about this TP. TP is from because each individual flip-flop has their delay. Okay, so if the clock frequency we are deciding and we are changing the input, definitely the flip-flop will also take some time to process it. So we need to consider the delay, internal delay of this flip-flop as well. If we are changing the input even higher than this one or faster than the delay of this flip-flop, might we will not get the output perfectly at this point. Okay, so in this case, the TP need to be considered. What is the propagation delay of that flip-flop? So if the propagation delay of flip-flop is very less, what it means, we can change the clock frequency frequently. Okay, but if it is very high, so we need to wait some time so that that flip-flop can process those inputs, and then it can give the output. Then again we can make the changes in the clock, and then it will process the output. So the flip-flop delay is equally important in the clock frequency decision. The third parameter is, like, suppose if we have provided some data input and the clock is activated, so like if we require some settling time, so settling time should be as small as possible. Okay, so if the data change is there, so clock should also change at the same time. So if it is like that, so we need to also consider the settling time, because at which state the data is going to change and the clock is going to change. So this time difference is also important while deciding the minimum clock frequency. Okay, so the clock frequency depends on that. It does not depend on the whole, because once this clock is activated and the data is enabled, then we can decide, okay, we have to process it. It does not matter how much time it is holding the data. So hold time is not important in the clock calculation, clock timing calculation, but the setup time is important, because that gives you the time difference between the clock enabling and the data enabling. And ideally it should be as small as possible. All the components, they should be as small as possible, like TS, TP, TNS, all these timings are should be as small as possible, so that you can apply the maximum frequency to the clock, to the flip-flop. Okay, so this is how we can consider. You got the answer?
Yes, sir.
Okay, fine. So this is how we can maintain the things. Okay. Perfect. So this is all about the timing, flip-flop timings. One more important thing that we should consider here is the race around condition. I just told you what is the race around condition. Suppose if I have we have already discussed these things before, but let me recall it again. Suppose I have a clock pulse having the width something like this. So this is the clock pulse width. Okay, and we know that in the RS flip-flop, if the clock pulse clock is activated, I'm considering the positive level triggered one. So this means the logic of clock is high and the duration is this much. Okay, so for positive level triggered, the flip-flop will be triggered if the level is high, like clock pulse is high. Okay, now suppose clock is high, and because in the race RS flip-flop, the output could be anything, either it could be 0 or it could be 1. In a small change in the input, that can flip the logic, or the output can be different. Okay, so there will be a probability, like initially, like clock is high, and if the output is changing from 0 to 1, this is one of the possibility that it could be done. But if the clock pulse is very high, the output, like in this small change in the input, output can, yeah, so this is the time which we can consider. This is the propagation delay. Okay, we have activated the clock, but we are getting output after certain period of time. So this time period is the propagation delay of the flip-flop, which we have already studied in the previous slide. Okay, once the output is logic high, okay, so I'm assuming that there should be only one change in the output during one clock pulse. So ideally this should be something like this, and then output can change after the clock pulse is disabled, something like that. Okay, so this is the ideal requirement, but in practical this is not possible if the clock pulse width is very high. Okay, so there may be the output can toggle from 0 to 1 to 0 again, even the clock pulse is activated and the clock pulse is not changing, it is same state at the same state. So the output could be like 0 to 1, it can toggle, and again it can, so this is what we can say the propagation delay of that flip-flop. Okay, so it can maintain this one, and again it can toggle for some period of time. So these are some of the ideally I wanted to maintain the logic something like this, but there are some toggling in between, there are some changing due to the race around condition. So this kind of problem we can call it the race around problem. Okay, so the race around problems must be avoided. Yeah, this is again TP, which is not desirable. So these are not desirable states. Okay, so how to avoid this problem? To avoid this problem, we can do one thing. Either I can reduce the pulse width of this clock. Okay, so if we are able to maintain, if we are able to reduce the pulse width, might be the toggling can be avoided, but 100% pulse width reduction is not possible, because now the clock, if I have reduced the pulse width, so the clock frequency will become very high. And if clock frequency will become very high, and in the last slide we saw the clock frequency depends on the propagation delay of the next state logic, propagation delay of the flip-flop, and the settling time, and these parameters cannot be reduced to 0. And if we cannot reduce to 0, this we need to have some finite pulse width of this clock pulse, and if we have a finite pulse width, then there may be a possibility then the race around condition can be there. Yeah, one of the possible, we can reduce it, we can definitely reduce the race around problems, but 100% cannot remove with the help of by reducing this clock pulse width. Okay, so because the clock pulse width depends on the many parameter we have just seen in the last slide, like it depends on the delay of the flip-flop, it depends on the delay of the next state logic, it depends on the setup time. So all these parameters decides like what should be the clock pulse width. Okay, so yes, definitely by reducing the clock pulse width we can remove this kind of race around problems, but 100% removal is not possible. Okay, so how to avoid this thing? The second, I just told you, so the first thing is like reduce the pulse width, reduce the pulse width. Okay, so this is one of the possibility. Second possibility could be like I just told you, because if we can make a circuit which can trigger during the transition from low to 0 and high to low, then that can also be utilized. So age triggering is one of the solutions that can be utilized. Okay, so age triggered kind of concept is also, I have already discussed this thing, so I don't need to discuss this one. So age triggered, age triggering is one of the solution to avoid this race around problem. Okay, so this is also one of the possibility. Either it could be the positive age trigger or it could be negative age trigger. And how to generate the ages? I just told you we need to utilize one differentiator circuit. Okay, so if I'm passing a clock pulse or this pulse train through a differentiator circuit, it will give you something like this kind of output. And if I'm passing through a diode, then I can make something like this kind of output. Okay, so if I want to get this kind of, then I need to use one differentiator with diode. If I want in the forward bias, here the differentiator and diode will be in the forward bias. If I want negative age trigger, in that case I need a differential amplifier and the diode in the reverse bias. Okay, so that I can get a negative age trigger. So the positive age trigger, negative age trigger, that depends like what is the direction of diode which we are using. Okay, so accordingly we can get it. So this is how this is the age triggering is utilized to remove the race around condition. Third condition is like the master slave kind of structure. Master slave structure means I can use a two flip flops. Okay, and the activation of both the flip-flops are opposite to each other. Okay, so if the clock is this is active high, so this should be active low. Okay, so this kind of arrangement is also solve the purpose of race around problem, because they will hold the logic for some period of time and then they can give you the output. So but the activation will be opposite to each other. Okay, so the third one is the master slave flip-flop. So master slave flip-flop is the one of the way to reduce the race around problem. There are three possibilities that we can utilize to reduce this problem. The first one is reduce the pulse width. And suppose if, yeah, we already discussed these things, so I'm not taking this much of time to explain this again. So reducing the pulse width will help you to write, suppose if you are reducing this pulse width, what does it mean? It means that the chances of flipping will be very less, like more than one flipping will be very less. So that can be avoided, but 100% that cannot be avoided. Might be if we have considered this much of clock width, and might be the output is changing at this particular time, and then again it changes. So this may create the problem. So even though we are reducing it, the width of clock to overcome this problem, but 100% cannot be overcome. And also you need a high frequency clock pulse, and might be to design an infinite frequency clock pulse is not possible. So the other alternative could be the age triggering I just told you. Instead of the level trigger, like triggering during this level, either logic high or logic low, we can consider either positive age trigger or the negative age trigger. Okay, so the positive or negative age trigger can solve the purpose. Like see here, might be like see if the transition is from low to high, and during this transition the flip-flop need to be activated. Okay, so this may solve the problem of the level trigger, like what was the problem with the level trigger. Okay, but again the pulse which we are generating, this may we cannot keep the zero rise time and the zero fall time. Ideally we need like zero rise time and the fall time, and that it should trigger. Okay, but this kind of pulse is not possible. So in that case, like there may be some degrading, and there may be some, if there is a possibility that the pulse decaying is taking too much time, so might be there could be a flipping in between as well. So there may be something. So to overcome that problem, there is one more alternative solution, and that solution we call it the master slave flip-flop. What this master slave flip-flop is, instead of a single flip-flop, we need to use two flip-flops, and the clock pulse in both the flip-flops are opposite to each other. One is the active high, and the second one is active low. Active high, active low means one is the positive age triggered and the second one is negative age triggered. Okay, so what will happen? It could be positive level triggered and negative level triggered as well. There is no problem. But yeah, so because the positive age trigger can solve the purpose, like the multiple change during a clock period or whatever the time period of the clock is. So one of the flip-flop will be activated during the positive age, and the second flip-flop will be activated during negative phase. So if we have provided some input to the set and reset input, and if the clock pulse is something like this, okay, because this is the positive age trigger, so this master flip-flop will be activated during this one. Okay, and because this positive clock pulse, and we have connected the same clock pulse to both of the flip-flops, the second flip-flop will not work. Okay, so it will hold the data, and once the next clock pulse will come, something like the negative clock pulse will come, negative kind of the spike will come. In that case, whatever the master flip-flop stored the data, that will be processed through this slave flip-flop. So this is how we can avoid this race around problem with the help of master slave flip-flop as well. So because both the flip-flops are triggered on different clocks, one is the positive age triggered and the second one is negative age triggered. So the clocking is different for both or opposite for both. So that will save the problem of that will solve the problem of trace around conditions. Yeah, if you see in the more detail, like suppose I have a JK flip flop and I want to make the JK flip flop based master slave flip flop. So how it could be done? Yes, if you can recall in the JK flip flop, this one of the input was connected to this input, and the second input this was connected with this one. So this was the this was the structure for the JK flip flop. But if I am using master and slave flip flop, yeah, so if you can see, this was the complete structure for JK flip flop, where we used to connect one of the input of this AND gate to the one of the output, and yeah, like in opposite output and so on. Okay, means the first AND gate input is connected to the QM bar, and the QM was connected to the preset AND gate. Okay, so this was the thing which we have seen. But if I want to make the JK flip flop based master slave flip flop, so individual component is not required here. So because I need to connect this, the output of the slave to the input of the master. So there's a difference here. What difference we have here? Like if I'm considering a single JK flip flop, in that case, this QM was connected with the reset AND gate, and the QM complement was connected with the set AND gate. Okay, so this was the structure of JK flip flop. But if I'm considering to make it the master slave JK flip flop, in that case, the structure will be something different, a little bit different than the original one. So here what we have to do, yes, again the output Q will be connected with this J, and the QM bar, like this, the Q bar will be connected to this one. So this is what a small change is needed, especially if it's not like if I'm consider master slave, so just cascade the two JK flip flop. No, we do not need to cascade only. We have to do all these kind of arrangement to make it the actual master slave flip flop. So this is how the master slave flip flop works. Okay, so yeah, if we talk about this the lower one is the level triggered master slave flip flop, and the upper one is the age triggered one. How we identified this, whether it is low age triggered or the level triggered? So let us try to identify. In the first circuit, if you see here, we have a triangle, and here we have a triangle and bubble both. Okay, triangle indicates the age trigger, and bubble indicates the negative one. Okay, so this one is a positive age trigger, this one is the negative age trigger. But if you see here in the bottom figure, in the lower figure, we do not have any block which is the differentiator block. We have not added any of the differentiator block over here. So if we have not added differentiator block, what it means, the lower circuit is the level trigger. Okay, so the below figure is nothing but this is the level triggered JK master slave JK flip flop, or JK flip flop based master slave flip flop. Okay, so this is all about the master slave flip flop and how it can solve the purpose.